made a lot of news, and he's going to present this right now.
Thank you. Thank you, Arya. It's a great pleasure to be here after 1 year of Encore. And today I'll talk about excuse me, my recent work with excuse me. with Xander Kelly from UC, and this is on strong bonds for arithmetic progressions, but at the core, it's a question about finding structure in dense subsets of integers. So the problem that we study is this old one due to Addition Turan, who asked this question in 1936. And the basic version is, how many numbers can we choose from 1 through n without any 3 of them being equally spaced? Right? You just have a bound on how many, the largest number you can pick, and you're trying to maximize the number of numbers chosen without any 3 of them being in equally spaced or forming an arithmetic progression. So this is a picture that I borrowed from Quanta, and it's kind of a nice illustration of some of the things that you might try. So for instance, you might say, okay, let me start with picking 1, 2. Right? I pick 1, 2 as my starting numbers, then I have to skip 3. Then, just as a greedy algorithm, I'll pick 4 and 5. Then I skip 6, 7, 8, 9, and so on and so forth. Thank you. Okay, and if you follow this strategy, then this greedy strategy tells you that you can pick about square root of the universe size many numbers without any 3 of them being equally spaced. Right? All of these trajectories kind of show the different greedy choices that you can make, and the orange one is somehow the best among all of these, at least when the maximum number is 40. Okay, and the general question, of course, is what happens when you just have an arbitrary n? And the best way to kind of quantify it is the following. What is the least size that guarantees that any subset with these many numbers will always have the desired structure, will always have 3 numbers which are equally spaced? Okay, and the only thing that we know about this subset A that we are looking at is that it's dense, meaning it has a certain size limit. So if you pick the yellow numbers, and there are 3 blue things which are equally spaced, and so on. The greedy strategy that we saw had square root n numbers, but that's not really the best you can do. It's far from the best. Behrend in 1946 said that there's a very nice, beautiful geometric construction. You don't follow a greedy strategy. A beautiful geometric idea gives you a much better set. You can pick almost n over 2 to the minus square root log n numbers, such that no 3 of them form this 3-term arithmetic progression. Okay, I'll just say 3 AP from now on. Just means 3 numbers equally spaced. And since then, there's been a lot of work on this question. Roth in 1953 kind of showed that if you have any set with constant fraction of elements, or roughly 1 over log n fraction, then you must have such a structure show up. This was exponentially improved by Heath, Brown, and Semeredi, and then Bourgain improved the constant in the exponent, and subsequent works improved it further. But but 10 years ago, people realized that 1 over log, that seemed like a barrier. If you have any set with 1 over log n, roughly 1 over log n fraction of the elements, then you have a 3-term arithmetic progression. And going beyond that seemed difficult. And this was overcome by Bloom and Sisask in a breakthrough work in 2020, where they went slightly over 1 over log n to the 1.01. Again, the quantitatively, like 1 over log n versus 1 over log n to the 1.0 doesn't make that big a difference, but qualitatively it makes a big difference. Like for instance, now you can use this to say that prime numbers have 3-term arithmetic progressions. Okay, because you get a lot more interesting sets from number theory which satisfy this property. Okay, and what we do in this work is to show that the true excuse me. The true answer must actually be close to Behrend's construction. Okay, we show that any set with roughly 2 to the minus log n to the 0.08 must have 3 numbers which form an arithmetic progression. And maybe the exponent is kind of still a little bit ugly, but the main takeaway is that maybe the truth is closer to Barron's construction and is an exponential improvement of the older ones. And just not our result, but also the most of the previous results, they say that you don't just get one 3-term arithmetic progression, you get many, many 3-term arithmetic progressions when you find one. And there's a way to quantify how many you find. Okay, so this is the history again. And let me take a detour from this problem and give kind of a very high-level sketch of what we do towards solving this problem and what the previous works did as well. And this will give an idea of one of the main techniques in this area, which is structure versus randomness. Okay, so the question that we have can be rephrased as follows. You have a subset A of integers 1 through n. All we know is that the size of the set is big, and you want 3 numbers such that satisfy the equation a plus b equals to c. Okay, if you think of this as an arithmetic equation, a plus b equals to c, then you can ask it not just over integers, but anytime you have an addition operation. Okay, so in particular, you can ask it over modular arithmetic. So now instead of thinking of numbers, just think of vectors, of trits, right? So I have n coordinates. Each coordinate takes a value from 0, 1, or 2. And you have the same thing as before. I have a set. The only thing that I know about this set is that it contains a large fraction of the overall size of the universe. Okay, in this case, there are 3 to the n strings, so you're measuring it with respect to 3 to the n. And we want 3 unequal numbers, a, b, c, from the set that satisfy the equation a plus b equals to c mod 3. So in every coordinate, you want them to satisfy a plus b equals to c, but arithmetic is done mod 3. Okay, you might wonder why 3. Well, if you do mod 2, it becomes a trivial question. And mod 3 is the easiest one, easiest non-trivial one. And most of the interesting things that we do kind of show up already here. And this has a history of its own. It's called the cap set problem. And if you know the game of set, you can think of this as a multi-dimensional game of set. So in the game of set, you basically have each card. Each card has 4 attributes, the shape, the color, the number, and the shading pattern. Okay, and you can encode it as a vector in 0, 1, 2 to the 4. And just assign 0 to, let's say, green, 1 to purple, and 2 to magenta. And then you can encode each card as a quadruple. And finding a set amounts to finding 3 cards which satisfy the equation a plus b equals to c. Okay, so this is basically asking, imagine you're playing an n-dimensional version of set. How many cards do you need to put down to guarantee that you'll always have a set? Okay. And the first thing that happens when you think of modular arithmetic is Barron's construction goes out the window. Okay, so as beautiful as the construction was, it uses some properties of integers, and it no longer works. You have modular arithmetic, right? Equations are easier to satisfy if you're doing modular arithmetic than if you're doing, just regular addition, right? Kind of that bears out very closely here, and the construction fails for a good reason. In a breakthrough work in 2017, Krutlev-Pak and Edgeworth and Geisweit showed that even exponentially small sets will have such patterns arising. Even if your set is very small, exponentially small compared to the size of the universe, you'll still find 3 such numbers, 3 such vectors. Okay, and their proof was algebraic in nature, and it doesn't carry to integers. And that's for good reason, because we know that such strong bounds do not hold over integers. In contrast, all the other works that I mentioned on the first slide, like Roth's work and so on, all of them also did first over modular arithmetic. Then they could push it to integers. Okay, they were analytic in nature. This is algebraic in nature. Maybe we'll see a little bit of this divide later. And what we do in this work is first give an analytic proof that kind of gets worse bound for the modular arithmetic case than what is known. But the point is that you can then push this technique to integers. So you have a new technique which gives a worse bound for finite fields or modular arithmetic, but then it extends to bigger domains. Okay, And subsequent to our work, Bloom and Sysask kind of found a cleaner way, very elegant way to push it to integers, and also to all finite abelian groups, in fact. Okay, so for the rest of the, maybe let's say how much time, like 5 minutes or 8 minutes, let me give a short description of how we do this, how we prove this statement over modular arithmetic. Again, there are 3 steps in the proof. The first step is what is called the structure versus randomness dichotomy. And this is kind of the bread and butter in this area. And I think this is one of the reasons why the 3AP problem has been important, because it often gives rise to techniques which are used elsewhere. And foremost among these is the structure versus randomness technique, which hopefully I'll say a few words about in a second. And there's this new notion of spectral positivity, which we introduce, which as a punchline allows you to convert kind of underestimation errors to overestimation errors. And finally, there's something called sifting, which I won't have time to talk about even talk about today. Okay, so let me talk about structure versus randomness. As a blueprint, it's basically very visual thinking. What do I mean by that? What are we trying to do, right? We have this subset A. All we know is that it's a big set, and we're trying to say something about this big set. So what is the kind of simplest big set you can imagine? I'll just pick the set at random. So each point gets included in my set with some probability, and you can do some back of the envelope calculations to say that if this is how the set A is chosen, then you must have many such nice 3APs. Why? There are many triples to start with. If you pick a random set, it's hard to avoid patterns, right? Because there are many patterns, and each one kind of gets included in your set with reasonable probability. So just because of that, you should have many, many patterns showing up. So wish one of our visual thinking is maybe we can extend this to say, maybe my set A is not uniformly distributed, but it's close to uniform. It's close to being random in some sense. Even then, I have many 3APs. Okay, of course, if I just have this, it's not a useful wish. We want to complement this with another wish. The second wish is what happens if you're not close to uniform. We want this sort of win-win analysis to say, okay, either you're close to uniform, in which case I'm done, or I'm not close to uniform, in which case I want to say that you have something very concrete that shows something nice that happens. In particular, I want to say that your points kind of lie in a nice substructure where your relative size has increased. You started out with some number of elements or some fraction of the elements in the overall universe. If you're far from uniform, then I can find an affine space or some structure where the relative size is better than what you started out with. Okay. If you can do this, then we can do induction. So idea is, either you succeed in the first step, or if not, I'm working with an easier problem now. And then repeat this again and again. Okay, so there are various ways to quantify, what these things are, but let's not worry about the quantification. Let's focus on this dichotomy. Right? Either we're close to uniform and we're done, otherwise we can do induction. Okay. And if you can do this, what's the template? You'll say, okay, I start out with my set A, working in the full space. I have some fraction of the elements. If I have a 3AP, I'm good. Otherwise, I go to a different set where my fraction has increased. Again, if not, again, my fraction has increased. Keep doing this. You can't keep increasing the number of elements forever. At some point, you need to stop. Okay, so you get some contradiction. At one of these steps, you need to find a 3AP. Okay, so that's the basic template. And, and people have been using this in this area for a long time. But the, excuse me. But the main thing we need to do is to figure out what these 2 steps are. What is the notion of closeness you need? And what is the structure that arises, right? So if your data is close to uniform in some sense, you want to say you have many 3APs. If you're not close, then something nice happens. Okay, so let me talk about what this first notion is. So closeness to uniform, I want to work with something very minimal in the sense of, okay, so what makes the definition work even? It's almost tautologically. So let's look at the set 2 times A, which is you look at all things in my set and multiply them by 2. Okay. So what are we interested in? We are interested in finding pairs A comma B such that A plus B is in the set 2 times A, meaning A plus B equals 2C, which is exactly the equation that we're looking for, right? So how can I quantify how many AB are there such that this equation is satisfied? Right? Instead of counting, if we think of ourselves as probabilists, the way to do the counting would be, maybe I'll pick A and B pretty much uniformly at random and check what is the chance that their sum lands in the set 2A. Okay, so here I'm writing X and Y for some reason so that I don't confuse them with the set A. So X and Y are being chosen uniformly at random from the set A. What is the chance that their sum ends up in the set 2 times A? Okay. And the set A is random and it's of size roughly delta fraction. So if it's close to delta, I'm happy. That means you have many such triples. Maybe it's not exactly delta, it's delta over 10. That's also fine for me. Okay. But now, what is the distribution of X plus Y? If I choose a random variable X and I choose a random variable Y, which is identical and independent, what is the distribution of their sum? Well, the distribution of the sum is usually nicer. Here's a plot of picking roughly, I think, 1,000 numbers from the range 1 through 10,000. And that's the blue line here. That's the set being chosen at random. So that's the PDF of X. And the magenta line is a PDF of X plus Y. So the distribution of X plus Y is smoother and nicer. And we of course know that when you add two random variables, it becomes a convolution in their probability density functions. Okay, so it's a nice operation that we know exactly what to answer, what to do with. And so what we are looking for is this equation. And the first step that we do is take a leap and not just ask this property for a single set 2A, but ask it for all big sets. Right? So find all sets, I want my distribution to be such that if I take X, take Y, add them up, the chance that they hit every large set is reasonable. As long as the set is somewhat big, you land in it with some high probability. Okay. So in some sense, I have my PDF here, and I want to say that you do not avoid any big set. If that's the constraint, then the set that you would pick should be the small value set. Okay. So let T be all the points where my density is taking small values. If there are a lot of such points, I'm in trouble. I won't satisfy the hitting property. Okay. So our notion of closeness is that you have your distribution X plus Y. Its average value is 1. The chance that it takes a value less than 0.1 is small. So you want it to be close to 1 always, but it's not close to 1. It's taking small values too often. That is bad for us. And that is our notion of closeness to uniform, that the density convolved with itself is anti-concentrated in this sense. Again, once you have this, almost from the definitions, you get that if you're close to uniform in this sense, then you have many 3APs. Okay, so that's the first part. Kind of, you have this divide that we are shooting for, and the closeness notion is this anti-concentration. Okay, so in the last 1 minute, let me tell you why this anti-concentration notion is useful, and this is where spectral positivity comes in. Okay, this can be in terms of picture. One way to think of this anti-concentration is forget the quantitative part, but imagine I'm actually plotting the PDF. Okay, and I plotted it so that the average value is 1. So I just scaled up the plot instead of everything being very tiny because you're working in a big universe. I scaled it up so the average value should be 1. And the bad scenario is when you have the function taking small values too often. But an arbitrary distribution, you can think of errors from the average value as upward errors or downward errors. Your average value is 1. Maybe I'm taking the value 0.1 too often. Maybe I'm taking the value 10 too often. Both are errors. Okay. And if you're an arbitrary distribution, you can have only downward errors with no upward errors whatsoever. Maybe your estimator is underestimating all the time and is overestimating only a tiny bit. And one of the main things that we exploit is that For a large family of distributions, this cannot happen. If your density is spectrally positive, you cannot have only downward errors. If you have downward errors, you must have upward errors. And spectrally positive just means that Fourier coefficients are non-negative. Okay? For any function, I can look at its Fourier coefficients. As long as it's non-negative, it cannot have only downward errors. Okay? And why is this okay for us? Well, why does the spectral positivity relevant for us? It comes for free. Because when you take a convolution of two distributions, the Fourier coefficients become products, and product of the same thing gives the square, which means it's positive. Okay, so you get spectral positivity for free, and then this part kicks in. Okay, so that's what I want to say about spectral positivity. It allows you to go from underestimation errors to overestimation errors, and then sifting is something that I haven't talked about. Okay. So in summary, we first give this analytic proof that gives a better bound for modular arithmetic. And then you can go from here to integers, which is quite technical, but uses similar ideas. Okay, this gives our main result. And a couple of open problems. First is extend this to 4-term arithmetic progressions. The other is to ask for, we're asking for 3 equally spaced points. But you can ask, excuse me. You can ask for such things in higher dimensional structures. So maybe you have a grid, I'm choosing a set of points. Can I find 3 points which are maybe like a triangle, like an isosceles triangle, like an equilateral triangle? Or one of the main things that people study is like right angle triangle. You can ask for all kinds of patterns. At what point can you guarantee that nice structures arise as long as you pick enough elements? Okay. So with that, let me stop. Thank you.
It was a great talk, Raghu. Now we all have to follow up on that talk, I guess. Is there any question for Raghu? Is there any question on Zoom? Maybe you can check.
Sure.
There is no question in the chat. Does the audience have any questions?
So basically, let's say I want to show that primes have 3-term arithmetic progressions, like infinitely many 3-term arithmetic progressions. The point is the density of primes is actually above 1 over log n. So it's actually, you need that slight advantage over 1 over log n to guarantee that, it's slightly worse than 1 over log n. It's like, little over 1 over log n. And once you have the Blumen's result, you can apply it to.
So the Fourier transform over finite fields. So like when you go to integers, what do you do?
Oh yeah, so our integers, all of this becomes like a caricature.
I see.
Because the first thing is you cannot do induction so nicely. There are no subgroups or subspaces to work with. But you can still do Fourier analysis, like basically look at Fourier characters or the complex group and everything. Things work out.
I see.
Yeah.
Okay. So it works out, I guess. Thanks, Raghu.